Because we're still in the circle at the second point. The first point is intersect.
Okay, well, it can go out and in and still be part of the set, or not part of the set.
Eventually put the stairs in the end.
Absolutely, you have to do it a few iterations to decide first whether it's going to. Anyway, so we scrap these two now, so I'll just rub them out. And then this is our second point now, see this blue one. And then we do the same for that one. We double the rotation angle. This, when I say double the rotation angle, let's just be clear on that. This is 0 degrees going from here to here. So we double the angle, we go and then that again, and then we go towards the centre. That's going to be about 0.7, so we do 0.7 squared, 0.7 times 0.7, and we have something like 0.7 squared. 7 squared. I've got a calculator there. You can see it would be more than, it would probably go about 0.3 or 0.4. So that would actually then go to about this point, and then we add the initial vector on again. The initial vector being from this point to this point. Anyway, to cut a long story short, what will happen is it will go round and round. It could like sort of spiral in like this, or it could go towards the centre. This is not accurate, don't quote me on this. And or what the alternative is, it could go out here, and it could go right out to infinity, and just spiral out to infinity. So it can do one of those two things. If it doesn't, if it sort of sticks around, it stays inside, that's part of the Mandelbrot set. If it goes to infinity, then it's not part of the Mandelbrot set. And so we colour that a different colour. And that way, that's essentially how to create the 2D Mandelbrot set, basically. So, we do that not just for this pixel, but for every single pixel. And then that's how to create it. So in theory, you can, that's basically, just to quickly say, when you double the angle and square the distance, that's actually equivalent of complex squaring. It's squaring a complex number. And then you add that's to the power of 2 bit in the formula, you know, z equals z squared plus c, that's the z squared bit when you rotate, and then go towards the centre. So going back to the presentation, what I thought of doing was simply applying this principle, just before we move on. This was created by Ivan Freeman. He made a program which it plots all the orbits, and it can actually see where the orbits travel. So this point here is sort of going in towards this point, so it's sticking around. So that point is part of the Mandelbrot set. How about this point here? Yes, that sticks around. It kind of goes in a strange star-shaped orbit. So that sticks around. If you were to try one from out here, it would go, and then kind of go off into infinity. And as you can see, that's outside the Mandelbrot shape. So this is a YouTube video. If you go to, again, it's on the paper, but if you go to the YouTube video he's got there, you can see how he moves it in real time. It looks really nice, actually, just to see that.
Which one is that on your paper?
You have, if I had a globe or a football, it would probably be easier, but you can, this is the initial point, and you can sort of travel round the back of this. You can any spherical object.
We can imagine a sphere.
You can imagine it. So it can just go round the back and then sort of round in a circle like that. So that's the great circle. It covers it goes through the North Pole and the South Pole. Oh, by the way, just to quickly say, because I'm not sure, I might be assuming that you know, this is obviously a sphere. This is the top of the sphere, so you're a bird's eye view. And hopefully you can imagine that.
Yeah.
So anyway, so there's one type of rotation where you can go around the North and South Pole. That's theta, or you can go around the white circles, phi. And there's two different rotations, and of course if you're familiar with you know, map coordinates, then of course the world uses this exact system where that really would be the North Pole. They're just spherical coordinates really, but Wikipedia has an entry on spherical coordinates. and all the maths is there. And sort of, why not just rotate around both of these angles? And so that was the breakthrough. And it turns out that there's someone called Rudy Rucker, American mathematician, computer scientist, and also a science fiction writer as well. And he thought of something very similar to this exact same idea well over a decade ago. And there was, I think, just a tiny error, a small error, but really he also kind of thought of this general idea, and it's the secret behind the Mandelbulb, basically. And this is what happens if you do, you know, I said there were two different rotations, where you go, you can either go around the North Pole and South Pole, or you can go around each of the discs.
Latitude and longitude.
Exactly, latitude and longitude. If any of you are familiar with latitude and longitude, that's what they are.
Yes, what's this one?
Exactly, this is one of them. This is definitely one of them. No, this is actually, this is, I think, theta. And the next one, remember that, you saw this earlier? That's what happens if you just do phi. You're only rotating on one of the angles. The trick is to combine them both together. And that's what you get. So it'll come round full circle again. And that's only power 2, and then, like I said before, Paul Nylander just did the simple extension of it to I and we've got incredible stuff. There's power 2 again, but with an offset. It creates a very, very similar. Strangely enough, if you put power 8 with a different offset, it still looks pretty much the same, but this is with power 2, it creates rather different shapes. All kind of distorted, and that's obviously the power 8 version. Of course, if you can put it not just to power 8, you can put it to much higher powers. This is power 16, and this is go on.
I'm just confused. Like, what is the actual? I mean, what is the actual equation you're iterating, or is it a function for the Mandelbulb?
Remember I showed you earlier that that takes on the.
Yeah, it was way too small. I think.
I'll come back to it. Back to it. It's basically based on spherical coordinates, where you rotate around theta and phi. I'll show you at the end.
Right.
I'll show you. So running out of time. So this is. Sorry. Not used to this now, so that's my excuse. Let's get back. There we go. So this is iterations where 1, 2, maybe 5, 100, say, that's only approximate. But you can see you increase the amount of iterations there. This is what happens if you increase the iterations on the power 8 Mandelbulb. It starts off with this kind of blobby shape, and then it gets more and more blobby. And then with the final one, it's very blobby indeed, and that's where there will be loads of details. Okay, this is inside, and you can see, I thought, oh, let's grow the iterations where you can add more and more iterations and see how it develops. So this is an example of doing that. There are parallels to the 2D Mandelbrot set. This shape here is called the, sorry, just a minute. This is, if you want to pass that around, that's just one of the shapes of the pictures for printouts and stuff as well. So this is in the 2D Mandelbrot shape. This is one of the features that you might see in the 2D Mandelbrot. And the 3D Mandelbrot has an equivalent to that. It's very detailed in a similar way. So of course it's 3D on the left, 2D on the right. And spirals. This is a 2D Mandelbrot spiral, and there's a kind of Mandelbulb spiral there on the left, which is...
When your 3D ones, the colouring doesn't seem quite as dramatic.
Right, okay. Again, that's based on, you know what I said about the surface is only one colour.
Yeah.
That's the main reason, but I'm going to show you a few more pictures later on which will hopefully correct at least partially that. You also get the Julia set as well, and this is an example of a Julia bulb, if you like, where you can have, I won't explain the details, but there's a Julia set equivalent. Let's rephrase that. For every point on the Mandelbrot set, there's an equivalent Julia set, and you can. This is one of the points on the Mandelbulb and its equivalent Julia bulb, if that makes sense to some of you at least, hopefully. And this is another Julia bulb and another. So there are loads of different Julia bulbs which correspond to every bit of the Mandelbulb. And this is a very, very nice object here. And it's a real photograph. This one isn't actually rendered. And it was created by, if I can just find the name, okay, I have his name in my notes, so I'll come back to that. But basically, you can visit his site. If you have a look at the third one from the bottom, mandelwork.deviantart.com, he has this picture in his gallery, and you can. It's a real picture. In fact, I've got one as well. So I'm just going.
Oh yeah.
Apologise.
Do these things have some perspective imposed on them, sort of arbitrarily or something, do they?
Sorry?
Do you sort of impose a perspective on these things at some stage?
What the images I showed you before?
Well, it's on 2D image, isn't it? But
this is 3D. This is photograph.
yes,
So,
but it's a 2D picture of a 3D object. It's perspective in there somewhere, isn't there?
Yes.
well, I presume there'd have to be a little bit of perspective if it's a photograph. But
It's not an object. It's just an image.
Well, it's a theoretical.
It's a 3D image, but not a 3D object.
Well, in somebody's head it's a 3D object, isn't it?
Isn't it the brain that's doing that?
it's actually a sculpture. It's a print. They got.
It's a 2D picture I can see there.
It's a photograph. It's just
So this is a 3D printed object?
yeah, exactly. They use a 3D printer and they print a layer of
That's not 3D, that's only 2Ds. I can only see 2Ds there.
on the screen. It means
If you photograph that sculpture,
Response up to the-
By computer.
okay.
I'm talking about 3D objects, not the photograph of it.
Okay. Hang on. There's a few ambiguities that could be. Okay. The formula is generated by a computer. The 3D data is generated by a computer. The printout is, of course, done by a 3D printer. But I think they converted it from the data to a polygon form first, if that helps at all. Anyway, so again, you can visit his site at the third from the bottom there. I'll see if I can find something. And also, here's an animation of cross sections which I've created. And this is taking multiple slices throughout the Mandelbrot object. Power 8.
This raises a question. If you were to if you take the normal Mandelbrot set and change the C with the Z-axis, so you would stack different Mandelbrot sets. We've seen. Would that be a true 3D set? You could
just
argue.
make a mountain.
No, not the mountain. Like if you're changing the C parameter, right? You're getting different characteristics.
C.
So
to create Julia sets, all the different Julia sets.
Yeah, for example.
What you'd actually get, something interesting, but it would have that smooth look, which I remember I sort of said doesn't have that lovely detail which I was looking for. It would kind of create lots of. Each slice would be very detailed, but then the slices forming together to create the tower, if you like, would be very smooth. You'd see all these kind of smooth looks, and it wouldn't have that lovely detail. Good question, though. Good question. So nice try. But that's another that's another way of creating a different kind of 3D Mandelbrot set, actually. Again, it wouldn't have that same. This is Mandelbrot.